the Kuiper belt. One day it will be ours, and it will be the gateway to the stars. Once humanity's footprint has touched all the worlds of the solar system, we'll be the final frontier. Colonization will almost certainly spread from Earth to Mars, Venus, Mercury, the Moon, and the asteroid belt. Then, as the decades pass, Mars and the Moon will end up hosting thousands of inhabitants, while the large moons of the gas giants will become destinations for explorers, settlers, and research outposts. And then the ultimate frontier, the one that will open the doors to the stars, the Kuiper belt. But why should we think of going to such a place, so alien to our way of life and conceiving the environment? What could be the advantages of such an endeavor? And furthermore, what technologies and strategies will we need to implement to realize this project? In this incredible video, we will try to answer these questions. And in the end, we will tell you what, according to us, will be the real reason that sooner or later will push our species to expand like a wave to the edge of the solar system. When we think about space colonization, our minds don't go much beyond the Moon, Venus, or Mars. At most, we consider the possibility of exploiting the asteroid belt, led by Ceres, and tend to ignore the fact that beyond the familiar boundaries of our solar system lie Ceres and the Edgeworth Kuiper belt, a region that for our species could represent much more than we can imagine. The Kuiper belt. Before delving into the subject, we must first explain what exactly is meant by this name. When we think of the solar system, we think of rocky planets like Earth, gas giants like Jupiter, natural satellites like the Moon, and asteroids orbiting between Mars and Jupiter. But the solar system doesn't end there. Beyond Neptune's orbit, the farthest planet from the Sun extends a vast region populated by millions of icy objects, which are probably what remains of the material used 4.6 billion years ago to build the solar system. This region is called, indeed, the Kuiper belt, named after the Dutch-American astronomer Gerard Kuiper, who hypothesized its existence in 1951, drawing on studies already conducted 10 years earlier by the Irish astronomer Kenneth Edgeworth. So much so that it would be more correct to call it the Edgeworth Kuiper belt. The belt extends to a distance from the Sun ranging from 30 to 55 astronomical units, AU, where $1 is the average distance between Earth and the Sun, approximately 150 million kilometers, and contains at least 100,000 objects with a diameter greater than 100 kilometers, although it is believed that there are many more, too small or too weak to be detected. The most famous of these objects is undoubtedly Pluto, the dwarf planet that until 2006 was considered the 9th planet of the solar system. But Pluto is not the only one. In the last 20 years, thanks to the technological progress of telescopes, many other objects of similar dimensions comparable to those of Pluto, 2,450 kilometers in diameter, have been discovered. Objects like Eris, 2,326 kilometers, Makemake, 1430, Haumea, 1595, Quaoar, 1086, and others, all with a diameter exceeding 1,000 kilometers. These objects are called KBOs, an acronym for Kuiper belt objects, and they are very diverse in shape, size, color, composition, and orbit. Some are round, others elongated, others irregular. Some are red, others gray, others white. Some are made of water ice, others of methane ice, and others still of nitrogen ice. Some orbit near the plane of the ecliptic, and others have highly inclined or eccentric orbits. Some have one or more satellites, while others are solitary. In short, KBOs are real worlds that tell us the story of the solar system and challenge us to explore and understand them better. The Kuiper belt is the true frontier of the solar system and represents a great opportunity for science and adventure. A frontier that, however, bears little resemblance to the solar system we know. American astronomer Fred Whipple said that if we want to continue considering the solar system according to the familiar representation still used in many textbooks, with the Sun at the center of a system of coplanar ellipses, it becomes really difficult to include in this context the remote, chaotic, and mysterious regions beyond Neptune. If, instead, we try to see it as a complex physical system in continuous interaction, with the Sun at the center of a huge sphere of influence that extends for tens of thousands of astronomical units, populated by a myriad of exotic objects and only a small minority of familiar objects located in its immediate vicinity, the known planets and satellites, then our vision of the system changes profoundly. Until 30 years ago, in fact, The existence of the Kuiper belt, as well as that of the more distant Oort cloud, were only working hypotheses, and until the early years of this century, the region beyond Pluto seemed inhabited only by a sparse representation of normal asteroids. So why colonize the Kuiper belt? At first glance, it would seem, and it is, a truly terrible and inhospitable place. What are we going to do there? So far from home. Then, just think that it is so distant that a radio signal from Earth, the Moon, or Mars would take more than 6 hours to reach any object orbiting in the belt. This means staying in touch with our roots by communicating at intervals of 12 hours, between question and answer. The distance from the Sun, on average 6 billion kilometers, is so enormous that the New Horizons probe, the fastest ever launched, from 2006 to 2015 took 9 years to reach Pluto at a speed of 58,000 kilometers per hour, a distance that even a hypothetical atomic-powered spacecraft of the near future will hardly be able to cover in less than 3 years unless there are extraordinary breakthroughs in the field. Methods relying on solar energy, such as solar sails, obviously won't perform well at such distances, leaving nuclear energy as the only practical option. Nuclear thermal rockets we could build now might have travel times, bringing them down to just a few years. More advanced designs could achieve further reductions, but the journey to the Kuiper belt would still require travel times comparable to a 16th-century circumnavigation of the Earth. On the other hand, nuclear pulse propulsion could easily reach 1% of the speed of light, even with early versions of the technology, which might not be sufficient for a feasible interstellar mission, but is more than enough for traversing those remote regions. A journey of $40, the average distance between objects in the belt, using a constant acceleration of 1g, thrusting forward for the first half, thrusting backward for the second half, thus providing artificial gravity without the need for a centrifuge, would only take a month with the spacecraft reaching 1.8% of the speed of light. This would make transit between colonies fairly straightforward and represent the dominant spaceflight technology in the outer solar system. The incredible distance will also have another effect, causing sunlight to arrive in the belt with an intensity 2,000 times weaker than what we experience on Earth. This means ambient lighting will be comparable to nighttime on Earth even in broad daylight. Perhaps a paradise for a vampire, but humans would find it very difficult to live in what would equate to a constant night. The solution might be to amplify natural sunlight through mirrors. The same type of mirrors used by concentrating solar power plants on Earth could be employed to focus sunlight in settlement contexts. Existing technology is more than capable of amplifying moonlight to make it as bright as sunlight, and should be suitable for amplifying incoming sunlight in the belt to make it as strong as that arriving on our planet. As you can imagine, it won't be a paradise by any means, but then, why would anyone want to live there? Despite many negative aspects, the Kuiper belt offers numerous advantages for colonization. Among the most important is ensuring a future for the human species in case of natural and cosmic disasters that might strike the Earth or the inner solar system. Chief among these is the most terrible and definitive, the death of the Sun. As we know, the Sun will not shine forever. In about 5 billion years, it will deplete its hydrogen reserves used for nuclear fusion processes, and its core will extinguish. Then, it will start collapsing, initiating helium fusion, a process that will force it to expand into a red giant. Our expanding star will first engulf Mercury, then Venus, and ultimately, in all likelihood, it will swallow and incinerate both Earth and Mars. However, the destructive blast of our dying star will certainly not reach the outer solar system, where Earth's exiles will have had ample time to relocate, enjoying an environment much warmer, brighter, and more suited to their needs. Yet, while these are indeed significant motivations, they may only concern generations in a distant future, rather than those of the present. The drive to expedite colonization of the outer solar system is currently propelled by the vast quantities of mineral resources present in the millions of Kuiper belt objects, KBOs, orbiting in that region. The combined mass of the entire Kuiper belt is estimated to be 50 times greater than that of the main asteroid belt, and KBOs are found to be much richer in volatile substances such as water and ammonia compared to regular asteroids, while still containing significant amounts of useful silicate minerals and metals. Moreover, being porous and undifferentiated, these bodies appear highly suitable for mining operations. Before moving on, don't forget to subscribe to our channel if you haven't already. Make sure to hit the notification bell so you don't miss out on our daily videos. Yet, practically speaking, where could the settlements necessary for mining activities be established? Colonists could inhabit the icy crusts and mantles of the dwarf planets, harnessing nuclear fusion and geothermal heat to extract minerals from the soft ice and internal liquid seas. When discussing dwarf planets, Pluto and Eris immediately come to mind. Now, it must be acknowledged that some problems with Pluto are glaringly apparent. It's extremely cold and extraordinarily distant. Transporting materials from Earth would be unreliable, thus all resources would need to be sourced locally, with only essential goods, such as plant seeds, arriving from Earth. Pluto has only 6.3% of Earth's gravity, which undoubtedly poses enormous risks to the health of colonists. Currently, we do not know how much gravity humans need to survive and reproduce successfully, but it is highly probable that it is much higher than what we would find on the surface of Pluto or any other body in the belt. Moreover, Pluto receives only a fraction of the sunlight we receive here on Earth, so relying on solar energy could prove problematic. However, Pluto also has an advantage over many other rocky celestial objects. It's so far away that even the bombardment of radioactive particles from the sun is minimized. Radiation is a danger often overlooked in the science fiction genre, but for true planetary scientists, radiation poses a significant risk when developing plans for future settlements. The idea that settlements could be built in a location with reduced radiation risk, which could be further minimized by isolating buildings with thick layers of materials such as lead or ice, is truly enticing. Gathering construction materials shouldn't be a problem. Pluto has a thick layer of water ice and some nitrogen that should be able to provide both water and air to human colonists and their plants. The almost complete absence of an energy source like solar power could be a bigger problem. However, there is evidence of cryovolcanism on Pluto. It's conceivable that steam energy could be tapped from within the dwarf planet if colonists manage to dig deep enough. And what's said for Pluto also holds true for Eris, the most massive object in the belt, with a surface gravity strength of 10% of Earth's. Eris's most valuable characteristic, though, is its highly eccentric orbit, capable of bringing it to perihelion at a distance of 38 Australian dollars from the Sun, which is practically Pluto's average distance, and aphelion as far as 98 Australian dollars. This ability to reach the outermost limits of the solar system makes it the ideal place to establish some sort of interstellar service station. Most icy bodies indeed have the materials available to produce missile fuel, and there's no reason to believe Eris is different. Furthermore, for the same reason, Eris is in a prime position to host an astronomical observatory to explore the Oort cloud and beyond. Of course, we're talking about prospects still very distant, of an undertaking that can only be realized by a highly evolved Earth civilization, already capable of traveling throughout the solar system and mastering nuclear fusion in every form, both to power spaceships and to tap into an inexhaustible source of energy. However, the idea is gaining ground among space travel experts that those extreme places could become much more than just a worthy destination for exploration for humankind. In that gigantic cluster of icy worlds, the most visionary minds are indeed glimpsing the possibility of using the myriad of ever more distant objects as a kind of ladder to climb step by step to reach the stars and extrasolar planets. It's already happened with the Moon. If our species hadn't had that convenient platform with a view of the cosmos represented by our natural satellite, we would hardly have dreamed of reaching Mars today. Without that convenient foothold, we certainly wouldn't have even remotely considered being able to make a single leap from Earth to the red planet. The gap would have been psychologically too great. And the same thing is happening now with the Kuiper belt and then with the Oort cloud, which stretches out into outer space until its peripheral comets almost blend in with those of Alpha Centauri. As far back as the 1990s, following this insight, astronomer Carl Sagan envisioned that over time there would be human settlements on the asteroids of the Kuiper belt and then among the comets of the Oort cloud, and that one day humans would even be able to settle on these small worlds and use them as spaceships to eventually leave the solar system and set sail for the stars. Even English physicist Freeman Dyson suggested in his writings that within a few centuries human civilization would move to the Kuiper belt and then make the big leap into the Oort cloud, first to reach the innermost comets and then, as happened in the past for the colonization of a large archipelago of islands, From comet to comet, they would reach the outer limit of the cloud. And from there, where the comet swarms of the Sun and Alpha Centauri almost merge, they would make the final leap. These are obviously projects to be realized on a scale of centuries, so any of our fantasies about them would surely be surpassed by the reality of a still very distant future. Many people believe that interstellar travel is impossible. Others say it's just incredibly difficult to achieve, just as 500 years ago a flight to Mars would have seemed to Christopher Columbus and other navigators. In fact, surprisingly, the ratio between the distances Earth-Mars and Spain-Caribbean is 80,000 to 1, roughly identical to the ratio between the distance Earth-Alpha Centauri and Earth-Mars. So if it took 500 years, since Columbus' time, for the technology to develop that is allowing us to reach Mars, then why not think that in another 500 years we will have already colonized the entire solar system and will be about to bring our colonies to the Kuiper belt and then to the Oort cloud? Generational timescales will be needed to undertake such a slow boat journey, but in the end, the colonists departing from the Kuiper belt will expand so much that the colonization frontline will be closer to another star than to the Sun. From there, perhaps for many centuries, their descendants will slowly migrate inward into a new solar system. In this way, human civilization could expand, very gradually, to the stars even if no dedicated crewed interstellar mission is ever launched. This opens up the next phase of the final frontier, that of other solar systems beyond ours. The last frontier of the solar system, the Oort cloud, will ultimately prove to be a simple launching pad into a broader universe of possibilities.